of silence.
Alright, we'll going for the heavy side. Alright, but anyhow, speaking of the sounds of silence, we'll talk about how sounds can be used to make silence here in a little bit. But anyhow, moving on. We had just talked about frequency and said that frequency is opposite of wavelength, inversely related. The shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. Now, wave speed. Wave speed has to do with how fast the wave is moving in a direction, okay? It does not directly, okay? It's a little different thing. Frequency is how many of these wavelengths come by per second. Speed is how fast from one place to another, okay? For example, all the electromagnetic waves, light and gamma waves, whatever, all travel at the same speed. We call it the speed of light, but technically it's the speed of radio waves, it's the speed of gamma rays, it's the speed of all of those things. They all move the same speed. The only thing that they're moving through, okay, they're traveling through, okay. So all go the same speed through, say, air, or same speed through a vacuum in outer space. In fact, technically, when we talk about the speed of light, it's the speed of a vacuum, because once it hits our atmosphere, it slows down from 300 million meters per second to maybe 299,999.99999 meters per second. Not so much that you would notice it, but it does slow down. If it goes through glass, it slows down even more. Okay, so the speed determines a lot about how fast it goes through. Now, this is different for the transverse waves, which are usually what I think of the electromagnetic waves, and for sound waves, which are compressional. If you're a transverse wave, that's our ones that go up and down, perpendicular to the direction it's traveling. This is like this. This would be like a light wave. All right. They travel the fastest in gases, then liquid, and they're the slowest in solids. So in other words, the less matter there is, the faster they travel. So in fact, the very fastest they travel would be through a vacuum. There's no matter at all to travel through, and so it actually goes fastest in a vacuum, and then gases, which are the farthest apart, matter, and then liquids, which are closer together, and then slowest in solids. Now, on the other first waves, which are like this up here, which are vibrations, things push against each other, it makes sense that those vibrations from one atom to the next, it works better if they're closer, the fastest in solids, okay, than in liquids, or slowest in a gas, which is air. So we actually hear things through the slowest medium. Now, granted, if they were going through solids, well, it's kind of hard to stick solid stuff in our ears so it could travel there. It's not necessarily saying that it will be clearer and so forth. It is saying it will travel fastest. So it will actually travel fastest. And it would be the slowest. And if it were in a vacuum, it would not travel at all, because there's nothing in a vacuum to vibrate. Remember, it has to vibrate or move things, squeeze things together, spread them apart. So if there are no atoms, then it can't travel. So if I was giving this lecture in outer space, you would hear this. And wouldn't that be nice and quiet? But it would be hard to study for the test if that's how the notes were. So sound waves also travel faster, since they're these compressional waves. They travel faster if the temperature is faster. If the atoms, remember, temperature has to do with how fast the atoms vibrate or move. So the hotter they are, the better, or faster at least, that the sound would travel through them. Okay, and so the formula that we have for the velocity of a wave, okay, is in your notes, but it's a velocity of the wave is equal to the wavelength times the frequency. Okay, basically, if the velocity stays the same, then if you have a long wavelength, then you'll have to have a shorter frequency, so it equals the same speed. But say it's going in a different medium and changes, then if you increase the wavelength and keep the same frequency, in order to have long wavelengths, still coming by just as fast, it would have to speed up and go faster for that to happen. Okay, so if you increase the wavelength and keep the frequency the same, it would increase the velocity. Or if you increase the frequency, how many waves are coming by per second, but make each wave longer, then that would also increase the velocity. All right. On the other hand, if the velocity is the same, and this part does not change, then if one of these goes up, the other one has to go down in order to keep it the same. And that's kind of what we talked about before. Now, another characteristic of wave we talked a little bit about earlier, but we need to do a little more, is amplitude. All right, amplitude. Oops. Tried to type about 5 things at once there, and none of them came up. So let's try that again. All right, amplitude. Basically, we talked about how, like this one has more amplitude because they're squeezed closer together. We said for a wave like these two waves, this one has greater amplitude because it goes up and down. For a transitional wave, that's transitional wave. For a compressional wave, it has more to do with the closer together and the farther apart they get, that's bigger amplitude than these. This is a low amplitude because they just barely get closer together and barely spread farther apart and barely get closer together. And we talked about a yell versus a whisper, okay, and that's what's the amplitude. So it has to do with the energy of the wave, and in terms of sound waves, it's going to have to do with the loudness of the sound. All right, we'll talk more about that under our sound waves, or sound notes. Talk about Roman numeral 6 on your notes if you're following along. The behavior of waves. There are some characteristics of waves that are true of all types of waves, and we'll talk about more of these as we talk about sound waves and then later light rays and stuff like that. Just for the record, we use the word ray and wave fairly interchangeably, and we'll do later. The first characteristic is if sound or light goes and hits something, it can bounce off. With light, this would be, say you look in a mirror, light hits the mirror, bounces back to your eye, and you see things in the mirror. For sound, it'd be like an echo. If you talk and you hear echo, 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 all that coming back, that's because sound waves are bouncing back. So reflection is when a wave strikes something and bounces off of it. Now, we pretend this is a mirror, and this is light rays, or it could be something else, and sound waves hitting it and bouncing off. Okay, where it's coming in to the mirror is called the incident ray or incident wave, whichever you prefer. Okay, remember we said we can use those two. Now, where it bounces off is known as the reflected ray or wave. Okay, now it doesn't matter about being top or bottom. I could draw it going in this way and bouncing off here, then this would be the incident ray, and that would be reflected. It can come, in this case, it comes this way and bounces off. Whichever one is coming to the mirror, that's the key thing, the arrow is pointing to the mirror, is going to be the incident ray. And the reflected ray is going to be the outgoing, or the one that's bouncing off. Okay, now there is if we were to draw a perpendicular line to the surface, this is just an imaginary perpendicular line down here, this would be called the normal, just for the record. Alright. If something is normal to something in, I believe it's geometry, it means it's perpendicular to. So this normal line is perpendicular to the surface here. If we drew a line there, this angle here on this side would be called, surprise, surprise, the angle of incidence. Alright, and the angle between the normal and the reflected ray on the other side, guess what? It's going to be called the angle of reflection. Okay, and so there is what is called the law of reflection. And it just says, what you can see right here, that the angle of incidence is always equal to the angle of reflection. So for example, this one can't come in at this angle and then bounce off at a different angle over here. It will always bounce off compared to the normal at the same angle as it came in. And that's just a law of how it works. All right. Reflection. And basically that when things bounce off, they'll always bounce off at the same angle. And that's kind of what you need to know about reflection for now. All right, another thing we need to talk about is refraction, not to be confused with reflection and some of these other words. It is but refraction. All right, refraction is more about when light or some other wave passes through an object. Okay, if this is the wave coming, it's a straight surface like that. Okay, when it hits the glass, let's say this is a lens right here, a glass lens. When it hits the lens, if you remember, light is a transverse wave, and it's going to go slower in glass than it will in air. So when this bottom part hits, it's going to go slower, but the top end is going to go faster. Okay, it's kind of like if you pull your car off the side of the road. The wheel that gets on the side of the road is going to be in gravel or grass. It's going to go slower, and it's going to try to pull your car off in that direction. Well, the same thing here. This end of the light ray is going to hit the glass first and slow down. This other end is still going the same fast, still going quickly through the air, and it's going to turn. Okay, and once it turns, now once it's all in the glass, it's going to go the same direction until it gets over here. And this time, the top is going to hit the air first, and it's going to speed back up because now it's going through air. So it's going to speed up, and it's going to tilt it even more. Now, I didn't show the tilt too much, but you can still see that these are now tilted more than they were when they were going through the glass. Okay, and the same thing would happen down here, just upside down in reverse. The top would hit the glass and slow down, so the bottom would go faster and it would tilt it up. Over here, the bottom would hit the air first, and it would speed up, which would tilt it some more toward the middle, and they would eventually focus back here. But that's refraction. Okay, it's when a wave bends because it's changing speed as it goes from the air into the glass, or from one medium to another medium. It can be air to glass, glass to water, water to matter. Any of those are going to cause it to change speed, and it causes it to bend. All right, and we'll talk more about that in a future date when we get to light, but that's good for now. Now, let's do two walls here with a doorway in the middle, and somewhere in here we have a light, and it's giving off light rays. Looks kind of like a little sun there, but you get the idea. Okay, there's a light bulb giving off light. Now, when it comes over here, the light doesn't make just a little square path going through here and everything over here stay in darkness. Instead, as it comes through the door, it tends to bend out. And so if you're over here in the corner of the room and we turn this light on in the next room, it will get lighter over here. Now, the farther away you get over here, the light gets, since it's curving out, it spreads out and it gets less. But the light actually bends. As it comes through here, it bends and bends out to the sides. Okay, it doesn't just go straight line, boom, so you have one little bright square where the door is and the rest of the room is completely dark. It actions, and so you have some light traveling off to the sides, off the edge. So when light bends as it goes through an opening like a door, or it could be around a corner, like a corner of a building or a corner of a hallway, okay, it bends, and that is called diffraction, not refraction. That's when it changes going through two different things. This is diffraction. All right, so it's the bending of light rays as it goes around an object or as it goes through the opening. Now, one thing we need to know about diffraction is the longer the wavelength, the better the waves refract. Okay, so the longer the wavelength, the better the wave diffracts. Okay, and so that's kind of an important thing to remember for that. We can talk about this with AM and FM radio. Generally, if you're in town, downtown, with lots of big buildings, the radio waves have to bend around. AM radio waves have longer wavelengths, and therefore they are more likely to bend, and it's easier sometimes to pick up AM stations when you're somewhere like that where it needs to bend around things a lot like that. All right, looks like that's where we're going to stop for these notes, and we'll finish up in the last one. I'll be glad to see you back for part 3.